Let's continue with example number 4. In this example number 4, we want to find the slope of the tangent line to a parametric curve. So the example says, find dy dx, which is the slope of the tangent line, for the parametric curve given by x equals a cosine cube of t and y equals a sine cube of t. So these are the set of parametric equations where t, the parameter, is between 0 and 2 pi inclusive. This a is a constant. And we start with the solution. Our first step will be to use the formula for dy dx. So we write use formula. And then the formula for dy dx, as we have seen before, is equals to dy dt over dx dt. So now, what is y? Y is here. This is the equation for y. Y is a sine cube of t. So we are going to take the derivative with respect to t of a sine cube of t. And on the denominator, it will be the derivative with respect to t of x of t, which is a cosine cube of t. A cosine cube of t. Now, on the numerator here, the derivative of a sine cube of t. Since a is a constant, then we can just remove it from the parentheses, and it will be a, the constant, times the derivative of sine cube of t. On the denominator, it will be a times the derivative of cosine cube of t. We continue. Now we can start canceling this a, because that's a common factor, and the next step will be to take the derivative of sine cube of t. The derivative of sine cube of t will be 3 sine square of t by applying the power rule here. But since this is the composition of two functions, the cubic function and the sine function, we need to apply the chain rule. So we multiply all this times the derivative of sine of t, which is cosine of t. Over on the denominator, we take the derivative of cosine cube of t. Again, we are going to use the chain rule there. So that will be 3 cosine square of t, and then times the derivative of cosine, which is negative sine of t. Now we cancel common factors, 3 on the denominator, 1 cosine on the numerator, and then 1 cosine on the denominator. 1 sine factor on the denominator, and 1 sine factor on the numerator. So we have dy dx, that will be equals to sine of t, that is left, sine of t, over cosine of t on the denominator, and then the negative sign which stays, that doesn't cancel, so we can write the negative sign in here. So that will be the answer, negative sine of t over cosine of t, which we can also write it by using trigonometric identities. This is tangent of t, and with a negative sign, of course, tangent of t. So the answer will be negative tangent of t. So this curve here, this parametric curve, is an important parametric curve. Our solution is done. This is the answer. But let's talk a little bit about this parametric curve. It turns out that this parametric curve has a special name, and that is called the Astroid. So let's make some comments about our solution. The parametric curve in the previous example, as we said, is known as the Astroid. So let's describe how we trace an asteroid. Number 1, let's consider a circle with radius a. And this circle is centered at the origin of a rectangular coordinate system. Number 2, inside this circle, there is another circle with radius a over 4. And let's focus on one point, on this point here, this point here, this point here on the small circle. As it rolls, as the small circle rolls, then it will describe an asteroid, whose graph will be this. That will be the graph of the asteroid. And then let's write the parametric equations again for the asteroid, which are x equals a cosine cube of t, y equals a sine cube of t, where t, the parameter, is greater than or equal to 0 and less than or equal to 2 pi.